Complex numbers. Complex numbers are numbers of the form z is equal to x plus yi, where x and y are real numbers, and I squared is considered to be -1. So the first part without I is called the real part, and the number attached to I is called imaginary part. We can place a complex number in the rectangular system as follows. We consider that y is the imaginary axis and x is the real axis. So if I have a point, any point, let's say z is equal to x plus yi, so in that case x is the first value and y is the second value. This is the y-axis, which is called the I-axis, the imaginary axis. So this particular point has 3 and 4, so this particular point can be written as 3 plus 4i. The number by itself without I is the number on the x-axis, or the direction on the x-axis, and the number on the other attached to I is the number on the imaginary axis, which is y in that case. Note number 1, every real number can be written as a complex number. Real number does not have that I, so z is equal to the number x. So for example, we can write number 3. Number 3 can be written as z is equal to 3 plus 0i. And all those numbers are gonna be on the x-axis. Imaginary numbers are on the y-axis, so y is equal, and we can write imaginary numbers 0 plus yi. For example, z is equal to -2i is on the imaginary axis. So if we plot our coordinate system, we can find this number that's a real number, and we know that this is x-y axis or imaginary axis. So x is equal to 3, 1, 1, 2, 3, and 0 on the y, x and y coordinates, 3, so those are the point. This is the point 3 plus 0i. So all real numbers are going to show up on the real number parts on the x-axis. And now imaginary numbers, just imaginary numbers, so it's -2i, so my x is 0, because this number can be written 0 minus 2i or plus minus 2i. So I have x 0, and I'm going down right here, so this point is -2i. Another thing that we would like to talk about, the modulus or the magnitude of a complex number. Z is equal to x plus yi is defined to be the absolute value is equal to square root of x squared plus y squared. And that absolute value is the distance from the origin to that point xy. So if we consider our coordinate system, the point x and y, the complex number, can be right here. Z is equal to x plus yi. So if I connect this with the origin, this gives me the right triangle. This distance is nothing else but my x distance, and this distance is nothing else but my y distance, y distance. So if I use Pythagorean theorem, this distance we can call it r, or we can call it the distance z. So I would have that this z square, or let's call it r. So I have that r square is equal to x square plus y square, or we can call it the distance z, the distance z squared. Okay, now I can take square root of both sides to isolate for z. Absolute value z is square root of x square plus y square, and that's what we have right here. So modulus, or magnitude, or the distance from the origin to that particular number, complex number. A complex conjugate. A conjugate of a complex number z is equal to x plus yi, is z with the dash on top, and it's x minus yi. And now let's see what is z times its conjugate. Let's try to work this out. So my z is this number, so I have x plus yi, and my z conjugate is this number, x minus yi. Now we can multiply this out, or we can use the formula. This is a plus b. So if we note, I have a plus b, and this bracket is a minus b. A plus b times a minus b is nothing else but a square minus b square. Was it like this, the formula? A square minus b square is a plus b, a minus b, or we can FOIL it, multiply this out. I'm gonna go with this formula. So I have the first term squared, so it's x squared, minus my second term square is yi squared, and I work this out. X squared is nothing else but x squared. yi squared is y squared and I squared. And we know that I squared from the definition is nothing else but 1, negative 1, by the definition of the complex number. So we have that this is equal to x squared minus y squared times minus 1. Minus times minus gives me positive 1. So x squared plus y squared. So if we look to the diagram, it's nothing else but the distance, right? Here was my point. Z is equal to x plus yi. Okay, if I connect this, here's my x, here's my y, here we call it the distance. So we know that Pythagorean theorem says that this is x squared plus y squared. So we have that the z distance was x squared plus y squared. And now if I substitute my x squared plus y squared is nothing else but z times z conjugate. So I'm getting that the z squared is z times z conjugate. So take the square root. So z is equal to square root of z times z conjugate, and which is nothing else but x squared plus y squared. And this we can keep in mind. That's the relation between the conjugate. Let's talk about polar form of a complex number. So we have definition that if r is a positive number and theta is between 0 and 2 pi, then the complex number z is equal to r plus yi can be written in polar form as that z is equal to x plus yi. We know the formula that x is nothing else but r cos theta. We can write this and find this from the diagram. If I plot my point, z is equal to x plus yi, then I can connect this with the origin, and I'm getting this is my x, this is my y, and this distance is gonna be called the r. So my theta is right here, the angle. So regarding this angle theta, this one is adjacent and this number is hypotenuse. Adjacent over hypotenuse is nothing else but cos theta is adjacent, which is x over r. We can solve it for x, so we can multiply times r, we can multiply times r, this cancel out, so I have that x is equal to r cos theta. We saw those formulae in polar coordinates. And the same I can use, and the same story I can use for my, if I use opposite over hypotenuse, gives me sine. So sine theta is y over r. Now we can solve it for multiplying times r, multiplying times r. So r sine theta is equal to y, or we can write x is r cos theta, y is equal to r sine theta if I rewrite this backwards, right? So we have those two formulae that we already know of, and we can take those two formulae and substitute for my x in complex numbers and for my y in complex numbers. So I substitute for my x and I have r cos theta plus, instead of y I'm substituting r sine theta, and then at the end we have that that I. So then I can just rearrange this and factor r out. So the polar form of a complex number is z is equal to r cos theta plus I sine theta. And that would be important to keep in mind. This is a polar form of the complex number. Z is equal to r cos theta plus I sine theta. We factor r out of the bracket from those two. So what's left is cos theta, and here is I sine theta. Now that angle theta that is formed between the distance of the complex number and the x-axis is called the argument of the complex number z. And we know that we can use Pythagorean theorem. R squared is equal to x squared plus y squared. Therefore r is equal to x square root of x squared plus y squared, which is nothing else but the distance. So the distance of the complex number is nothing else but r. This is my z. Let's do example 1. Plot each point given in polar coordinates, -1 plus I. I think the question is not stated properly. Plot each number, this number is not in polar coordinates, and then write it in polar coordinates. Plot each number, plot each point, and write it in polar coordinates. Express each argument in degrees. Express the argument in degrees. In degrees. So the first number we have -1 plus I. So this is my z is equal to -1 plus I. So the number by itself is x. The number by I is y. So we can plot it. We have -1 and 1 on the y-axis, so my point is right here. This is the point -1 plus I. So to write it in polar coordinates, we need to have r and theta. Find r and theta. R, we know how to find it. We can use the Pythagorean theorem because we can connect this triangle. So r is equal to x squared plus y squared. My x is non-1, so r squared. So r squared is -1 squared plus y is 1. -1 squared is 1. 1 squared is 1. So r squared is 2. Therefore, the distance r is square root of 2, plus or minus, but we choose positive, treating this as a distance on the same side. Now, we need to find the angle. So we are looking for this angle. But from this right triangle, we can find the reference angle first, and then find the angle that we are looking for. So using this right triangle, we can find the reference angle. Having this distance is 1, and this distance is -1, but we can always treat as 1, since reference angle is always positive. So regarding this angle, this is opposite. Regarding this angle, this is adjacent. Opposite over adjacent is tangent. Tangent theta is y over x. This is my y distance, x distance. So tangent theta is, we can go -1 over 1, which is -1, or we can treat this as a reference angle, so tangent is 1. We can have -1 actually, and then use the chart as we were doing this before. So tangent is 1, +1, +1 for reference angle. Tangent is 1 is pi over 4. They ask us express in degrees, so we can use 45 degree. Theta reference is 45 degree. If you find this from your calculator, tangent -1 would give us -45 degree, but we know that reference angle is always positive, so that's why we keep +1 as a reference angle for 45 degree. Now my whole angle is 180 minus that reference angle. That's gonna be my angle, right? So theta is equal to 180 degree minus 45 degree, which gives me 135 degree. 180 minus 45. So now we only need to write the polar form. Let's write down the polar form. We know that this is z is equal to r cos theta plus I sine theta by the definition of polar coordinates of the complex number. So now we can substitute what we have. My r is square root of 2. My cos theta is 135 degree plus I sine 135 degree. And that's the polar form of that complex number. Let's do B of that example. Now we stated this question correctly. Plot each number and write it in polar form. Express the argument in degrees. And now we have the number complex number 3 minus 4i. So we have that z is equal to 3 minus 4i. We can plot it. We know that the first coordinates is x, second coordinates is y. So we are plotting 1, 2, 3 and negative 4, 1, 2, 3, 4 right here. 3 minus 4i is that point. So we can connect this with the origin, and we will be looking for this angle. This is the angle, always positive angle for to express in polar form. We can find the reference angle if we make the right triangle. That reference angle right here. So we can use that this distance is 3. We can treat this distance as 4. Distance is always positive. But let's first find r. So r square is equal, now r. We are using this right triangle right here. So r is 3 squared plus 4 squared. Can be negative 4 squared, gives me the same. So it's 9 plus 16. So r squared is 25. R is plus or minus square root 25, which is plus or minus 5. But r is the distance, so we keep r as positive. And it's on the same size of pole, not on the opposite. Now we can find the reference angle. Regarding this angle, this is my opposite. This number is adjacent. Opposite over adjacent is tangent theta. Opposite is 4. Adjacent is 3. We don't go with negative because we are looking for reference angle in this right triangle. And we treat this as a distance is positive, distance is positive. So theta reference. We don't have this in our chart. We don't have the value 3/4. If we look at our chart, we don't have the value, 4/3. So we need to take the tangent inverse and get approximate value from calculator. Tangent inverse, if I take tangent inverse of both sides, 4/3. Now use your calculator. Make sure you are in degree mode. So when I punch this on calculator tangent inverse or 4 divided by 3 gives me 53.1. So we write it to the whole degree. It's approximately 53 degree. Make sure you are in degree mode. So if this red angle on my diagram is 53, what is that angle? We know that the whole rotation is 360 minus 53 is gonna be my angle. Theta is equal 360 degree minus 53 degree, and that gives me 307 degree. So now we can write the polar form of a complex number, which is z is equal to r cos theta plus I sine theta. That's the polar form of a complex number. We can substitute the given what we have. So this one is 5 cos 307 plus I sine 307, and that's the polar form of the original complex number. If we punch this on calculator, the first we should get 3. We should get this number if we perform this. Cos 307 and then multiply times 5 should roughly gives me 3. And the same situation here, I should get negative 4. do one more example. This same example. We want to plot this point and write the polar form of that point. So this point z is equal to -2. I don't have I. I'm going to write 0i. So I'm going to plot this point. First is x, this is y, -2. Right here is the point -2 plus 0i. And we are looking for this angle. So the distance from the origin r, is nothing else but 2. We can see this from the graph, but we could have gone and used the formula x squared plus y squared and find the same way. But because we don't have triangle, I would not recommend. I would just write that r is 2. r is 2 is the distance from the origin to my point, which is 1 and 2. But we can use those formulae too. And then the angle theta is nothing else but 180 degree. We see this from the diagram. So then we have the complex form z is equal to r cos theta plus I sine theta. So my z is equal to 2 cos 180 degree plus I sine 180 degree. That's the polar form of the complex number -2. That complex number is a real number. It's on the real axis, imaginary axis. So example 2. So far we were changing from a rectangular form to polar form. Now we would like to change opposite. We have the polar form. Write each complex number in rectangular form. This is polar form of a complex number. We need to write in the rectangular form. Rectangular form is nothing else. Z is equal to x plus yi. So we can keep going z, but nothing else. The easiest way is to just multiply this out and work this out. So I have 3 times cos 210 degree plus I sine 210 degree. When I work this out, cos 210, we can punch or we can find the exact value. So if I keep opening, here is 90 degree, 180, and then 270 right here, and then 360, and we started with 0 as well. So 210 is the angle up to here. What is my reference angle here? 180. How much more I need to go to get to 210? Nothing else but 30 degree. So my reference angle, theta reference, is 30 degree. We know that cos, sine, and all trigonometric functions are equivalent to the reference angle up to the sine. So add sugar to coffee. In the third quadrant, only tangent is positive. Both of them are negatives. So this is equal to 3 times minus cos of the reference angle, 30 degree, plus e times minus sine 30 degree. That minus comes from the quadrant. In the third quadrant, sine and cosine are both negative. Reference angle is 30 degree, and this is from the quadrant. Only tangent is positive. Now we need to use the chart. To find the exact values. So sine 30 degree is 1/2. Z is equal to 3 times minus 1/2 plus I times, sine 30 degree is 1/2, so we have here negative 1/2, but cos 30 degree is root 3 over 2. So here we have root 3 over 2. Now we can multiply out and work this out. So we can distribute this 3. So we have that z is equal to 3 times minus root 3 over 2. And then I have minus I times 3 times 1/2. 3 is like 3 over 1. So we can write that z is equal to minus root 3 over 2 minus I 3/2. So we should have write the I in the back. So z is equal to minus 3 root 3/2 minus 3/2 I. Here multiplication I can go to the back. One more example. Write each complex number in rectangular form. So as before, we are solving this. This is my number, and we need to find the angle. So 5 pi over 6, we have 2 cos 5 pi over 6 plus I sine 5 pi over 6. Okay, 5 pi over 6, here is pi. Pi in terms of 6 is nothing else but 6 over 6 pi. So 5, 6 is, we are a little bit short to 6, 6, right? So this angle is right here. How much short we are? From 5 to 6, 1, right? 1, 6. So this one is 1/6 pi or pi over 6. That's my reference angle. Theta reference is pi over 6. Now we use the chart add sugar to coffee. So only sign is positive in this quadrant. So this is equivalent to sine and cosine of reference angle up to the sine. So cos is negative and sine is positive. So we have 2 times cos is negative minus cos of my reference angle pi over 6 plus e sine is positive sine of my reference angle pi over 6. And now I'm using my chart that cos pi over 6 is root 3 over 2. So we have 2 times minus root 3 over 2 plus e times sine pi over 6 is 1/2. So we can distribute the 2. This is equal to negative 2 times root 3 over 2. This is like over 1 plus 2 times e times 1/2. This is over 1. 2 and 2 cancel out. So that this is equal to negative root 3. 2 and 2 cancel out plus I. That's my rectangular form of this complex number.